hopefully we'll get up to pH scale, but we'll see how it goes. Okay, so this is chapter 2. We will not do a lab on this. The lab today is going to be the rat dissection. So nobody wore their Prada or anything like that, right? You know, I'll give you a break, have a snack or eat some lunch, and then we'll come back. And I know I have fetal pigs in the refrigerator. I did not see the rats, but I know I have them down the hall as well. So I might take both out. We'll see how it goes. But I will generally take out a male and female of each. I always leave some benches without any organisms on them. So if you absolutely did not want to cut anything, you don't have to. You can, you know, go sit at that bench if you want to. But after the dissection is done, I will be going through each of the specimens and pointing out the structures that I feel are nice on those dissections and that you should take note of, because I will ask you questions on them on your quiz, which I think is next class, and on your lab practical coming up. So I will go through the dissections at the end, and if you don't cut anything, I hope that you will at least observe, you know, the identification of the structures. All right, so we'll look at chemistry. In chapter 1, we talked about the levels of biological organization. And I said that we were going to start at that very top level, the smallest level of organization, which were the subatomic particles. Okay? And we would use those subatomic particles to put them together to make up atoms. We're going to bond those atoms together to make up a molecule or a compound. And that's pretty much this chapter. It's dealing with the atomic level of organization, going from subatomic particles to atoms to molecules. We did that amoctoso, that little saying that I explained to you guys. The amoctoso, we're just going to cover that first part of it. Okay? And then in chapter 3, we're going to get into the cell and everything. So looking at the subatomic particles first, most people will know that there are 3 major types of subatomic particles. The protons, which have a positive charge, neutrons, which have a neutral charge or no charge, and the electrons, they have a negative charge. The protons and the neutrons are held here in the nucleus of the atom. So if this is one atom, let's say this is hydrogen, the protons for hydrogen would be here, as well as the neutrons. Okay? The electrons would be here in what we call the electron orbital. Sometimes we call this the shell. Electron shell. So the electrons are outside the nucleus, where the protons and the neutrons are inside the nucleus. So we have a positively charged nucleus, and we have a negative charge on the outside of that. Does that make sense?
Yeah, the hydrogen is probably not the best example.
Yeah, we're going to get to that. Good, that's good. And that's good, Odette, because Odette took my Bio 105 class, so I know he knows this. And if you took Bio 105, or even if you took a chemistry class, you might remember that hydrogen does not have any neutrons. It's one of those exceptions to the rule, of which there's many times there's an exception. So if this is hydrogen, then there is only protons here inside the nucleus. You're exactly right. There is no neutrons in hydrogen, so that proton is lonely in the nucleus. And there's an electron orbiting that nucleus in the electron shell or the electron orbital. The other thing that you might remember is the number of protons, hydrogen here has 1, is equal to the number of electrons. You really can't see from this diagram, and this diagram isn't the best diagram in the world of hydrogen, because they're not showing you the electron in the electron orbital. And they're really not even telling you what's in the nucleus. They're just showing you the basic shell model of a typical atom, where you see the nucleus in the middle and the orbital on the outside of that nucleus. So the protons that are positively charged equal the number of electrons. If hydrogen has, and it does, 1 proton, then how many electrons would it have? 1. If this particular atom, atom whatever, has 5 protons, then how many electrons would it have? 5. It's got to be the same. And for that reason, the positive charges equal the negative charges. So if we have 5 positive charges and 5 negative charges, then what do we get all together? Nothing, right? Neutral. We end up with neutral, nothing. No charge. An atom should have no charge because the positive charges should equal the negative charges. Protons equal electrons. In an atom, a little bit later we'll talk about ions, which are a different story. But in an atom, protons equal electrons. So most common atoms, I said hydrogen. Carbon is another one that we'll be talking a lot about in this course. Carbon has 6 protons. So how many electrons? 6. Okay. Oxygen is another one. Oxygen has 8 protons. How many electrons? 8. That's really easy, right? This should be really easy. Okay. Protons, positive charges inside the nucleus. Electrons, negative charges around the outside. And of course, the periodic table is in your textbook. You do not need to memorize it. In general, I will give you enough information as applying to an atom as you need to answer the question. So if I want you to calculate the number of electrons, I'll probably give you the number of protons. If I want you to calculate the number of protons, I'll probably give you the number of electrons. So you don't need to go back and study the periodic table and how it's arranged and the the metals and the non-metals and all that. You don't need to do that. We'll mostly be talking about carbon, hydrogen, oxygen, and nitrogen. Those will be the atoms that we spend most of our time within this chapter and further chapters talking about. Carbon, hydrogen, oxygen, and nitrogen. And yes, you should know what those abbreviations stand for. Calcium, Ca. Phosphorus, E. Potassium is K. Sulfur is S. Sodium, chlorine, magnesium, and Fe, iron. I'm assuming that most of you know a good majority of these. So at least these atoms here and the abbreviations listed here, you should know. We'll be looking at these throughout the course. All right, done that, that's fine. We'll talk about that as we go. You have the words in front of you, so I don't need to leave them on the screen. Easier for me to just use the picture. So I said that there was the protons and the neutrons in the nucleus of the atom. You can see them clearly here in this diagram. You can see that there's some red dots and there's some blue dots. Protons and the neutrons. Now the electrons here are orbiting that nucleus, and this is called the electron cloud model because the electrons are moving so fast around, it's like a blur. It's like a cloud. You don't really see them still. We won't be dealing with this one. Right? We won't be looking at the atoms arranged that way. We'll be looking at them more like this. So you can actually see the electrons in the electron orbitals. It's not going to look that much like a blur like the first diagram. So here you see the protons and the neutrons in the nucleus. You can see this orbital has 2 electrons in it. The 2 black dots are electrons. And this orbital here has 4 electrons. Does everyone see that? Okay. There's 2 electrons taking this path around the nucleus, and there's 4 electrons in this path. Right? It's just like an orbit, like a ring. You know, Saturn has rings around it, the planet Saturn. Okay, so it's like this path, this ring, that these electrons are gonna move in. And they're really not gonna move from one to the other. Pretty much gonna stay set in that path. This first orbit, this first orbital, the one closest to the nucleus of the atom, has only 2 seats within it. It can hold only 2 electrons. So you will not see 3 here. Okay, that's something wrong. Only 2 in the first orbital. In the second orbital, we can have up to 8 electrons. We will usually not go beyond the second orbital. We might go to a third, and with that third, we will only talk about 8 electrons being in the third orbital as well. That will be our max. You are not going to have to draw any of these, but if I have a drawing, you should be able to analyze it. We'll be able to identify the electron, the protons, the neutrons, the nucleus, the orbitals, how many orbitals are there, and so on. But you won't have to draw it. I will not give you one with, 5 electron orbitals, 53 electrons, things like that. I won't do that. We'll stick with generally 1 orbital or 2 orbitals. Maybe we'll do 3, especially when we talk about ionic bonding. We'll do 3 a little bit. So I can have 2 electrons in the first orbital. Those seats are going to fill up first. It's like the seats closest to the stage. Those fill up first. And then we're going to move to the outside, the second electron orbital. And those seats are going to fill up. And then we would maybe need a third. We have got more electrons coming to the party.
So only when you get 8.
But only when we get 8 in the second,
Yeah.
right? So if we were talking about an atom that had 11 electrons, if there's 11 electrons, that means 2 are going to be here in the first, 8 are going to be in the second, and then I would need a third, right? I would need 1 more row, but 1 more seat for that 1 electron. Yes, with me? Good, yeah? Okay. So what happens if we don't have a full outer electron orbital? Then we say that the atom is not stable. It's not comfortable. It's not a good crowd. Okay, so we want to have a full outer electron orbital in order for the atom to be stable. And how does an atom become stable if it doesn't have electrons enough to fill its own seats?
Ions,
It's
compounds.
friends, right? It has friends come over. And that's when we have bonding coming. And we're going to talk about 3 types of bonding: covalent bonding, ionic bonding, and hydrogen bonding. Everyone's okay so far? Very colorful diagram. Many different atoms that you can see here. So here's a sodium atom. Sodium. The nucleus of the atom, they're showing you there's 11 protons. So how many electrons should there be? There should have been a greater, more loud answer than that. Okay. 11 protons, so 11 electrons. And if you count up the black dots, you should count 11. Did they do it right? Because sometimes they get it wrong, you know. Even after the 15th edition, whatever it is, sometimes they get it wrong. So we've got 2 electrons in the first orbital. We have 8 in the second. And then we have 1 in the third. Our sodium atom. Now notice this atom, because it's not hydrogen, has neutrons. The little N with the 0, that means a neutron. Neutral, no charge. And there's 12 of those inside the nucleus. It is not equal to the number of protons. It is not equal to the number of electrons. Sometimes it just might be the same number by coincidence, but it's not equal. Protons equals electrons does not equal neutrons. Separate formula altogether. We could use this to determine what the mass number of the atom would be. The mass number is the mass of the nucleus of the atom. how many grams is it? How much does it weigh, in other words, if we were to take the mass of it? And the very simple mathematic procedure that you do to calculate the mass number is just to add the protons plus the neutrons. So if you add 11 plus 12, that will give you the mass number of the sodium atom. And what is it? Should not be rocket science. You should not need a calculator for this. It's, yes, 23. Mass number of sodium is 23. Now the other term that we can use to describe an atom, aside from mass number, is the atomic number. And this is how we arrange the atoms on the periodic table by atomic number. Essentially, it is just the number of protons in the atom. So the atomic number for sodium is 11. And we have our first formula. The first thing that you should memorize if you don't know this yet. The number of protons equals the number of electrons, you know that already, equals the atomic number. All three numbers equal each other. So if I give you the number of protons, you can give me the number of electrons and the atomic number, just from that one piece of information that I gave you. If I gave you the number of electrons, you should be able to give me the protons and the atomic number. Yeah? Good. The other formula that I said was for mass number. What's the mass number formula? Protons plus neutrons equals mass number. And you should be able to rearrange that. You know, this is not rocket science. If I told you that there were 11 protons and the mass number was 23, then you should be able to give me the number of neutrons. Do I need to write it? Right, good. So if I wanted to calculate the number of neutrons, then I would say mass number minus the number of protons. In this case, we have 23 as our mass number. We have 11 as our number of protons. So the number of neutrons is going to be 12. Good, Melissa. I mean, we could write it out like algebra equation, but it should just be kind of a logical thing that you just think about it in your head. 3 orbitals, 1 nucleus, protons and neutrons inside the nucleus. At the very top, you can see hydrogen, and now it's drawn correctly, by the way. So in the center in that nucleus, you see the 1 proton. And in the first orbital, there's 1 electron. So what's the atomic number for hydrogen? 1. Then using the formula that we were just talking about for mass number, what's the mass number of hydrogen? Good. So what's the number of neutrons then? Right. So if there is mass number of 1, and we have 1 proton, 1 minus 1 is 0. Then the number of neutrons in hydrogen is 0. It's the only atom that has 0 neutrons. The job essentially of a neutron, in very simple terms, is to make the peace between the protons, the positive charge in the nucleus, and the electrons, the negative charge in the orbitals. Like, make the peace. And because hydrogen only has 1 and 1, we don't really need to have a neutron there. Bless you. But as we move anywhere up from that, we're going to need some neutrons. Kind of like a buffer. Give me a little bit of space. It's too many people in the room. It's too crowded. All right. Questions on any of this? You don't need to memorize all of these. I'm not going to show you one drawing and ask you, is this iodine or chlorine or sodium? Hydrogen, you should know. Carbon, you should know. We'll be talking about those often. Sodium and chlorine, we're going to look at them again, but I'm not going to have you identify those atoms. Take a look up here at carbon. I didn't wear high enough shoes today to point to that, but so how many electrons are in the outer electron orbital for carbon? Outer electron orbital?
3.
Ooh, there's a lot of...
4.
Okay, so I said outer, meaning the most outside, the furthest away from the nucleus. And in the case of carbon, that's the second orbital. So how many electrons are in the second orbital?
4.
Oh my God.
Do I have my glasses on today?
On the outermost.
It's
Let's
4.
see. 1,
It's 4.
2, 3,
Yeah, it's 4.
4. 4. Okay? You guys all right? You had your Wheaties this morning or whatever? All right, so 4. 4 electrons in the outer orbital. Everyone agrees? Okay. Is carbon stable the way that it is then?
No.
What do we want to have?
8.
We want to have 8 electrons in that outer electron orbital. And if we don't have 8, in this case we only have 4, we still need 4 more, then the atom is not considered stable. So we're going to have to bond. Carbon's going to call some friends over in order to gain its stability. And it could be simple as 4 hydrogen atoms coming over to carbon. The 4 hydrogen atoms come over to carbon, and each of them bring with it an electron. That means we have 4 electrons from 4 hydrogens coming to join with those 4 electrons from carbon. Then we're going to have 8 in the outer orbital. That's carbon bonded to 4 hydrogens. I don't know if I have a picture of that, but I certainly can draw it if I need to. We'll see. You can skip further along if you want to see the picture, but it's in there. Here's what it looks like. Here's carbon and the 4 hydrogens that came to visit carbon. And the bonds that form between the hydrogen atom and the carbon atom, hydrogen atoms, I should say, and carbon atom, those are covalent bonds. One of these electrons was carbons, and one of these electrons was this hydrogens. So these sharing of these 2 electrons is a covalent bond. And we're sharing 2 electrons between these 2. We're sharing 2 electrons here, 2 electrons over here, 2 electrons over here. We're sharing 4 pairs of electrons, right? And just like before, where we had the electron orbital and the electrons were moving within that space, in that orbital, these electrons, these 2, are not only moving around this orbital, around hydrogen, but they're also moving here, around carbon's outer electron orbital. So we have 8 electrons rotating here around carbon. Now that orbital's full. And we have 2 electrons rotating here around hydrogen. Now hydrogen is stable as well, because hydrogen had 1 electron. Remember, first electron orbital can hold 2, so it's not stable by itself. But now it has 2 rotating around it. It's stable. This hydrogen atom, same thing. It has these 2 rotating around it. Right? We're sharing these electrons. They're rotating around hydrogen, and they're rotating around carbon. Don't get confused. I don't want you to think that the 8 electrons are rotating around each hydrogen. That's not happening. The 8 electrons are rotating around the carbon, and 2 of those 8, every once in a while, right, are rotating around that hydrogen. And all this is happening so fast that it looks like a cloud. That looks like, a blur of movement. But we were able to take a snapshot of it and freeze it. Looks like this. So this molecule, it's more than 1 atom. We're putting atoms together. It's carbon and 4 hydrogen. This molecule is now stable because all of the outer electron orbitals are complete. With me? Yeah? And if we were to draw this kind of shorthand method, it would look like this, where I have C representing my carbon atom with its orbitals, and H representing the hydrogen atom with its orbital, and the line connecting the two represents the sharing of a pair of electrons. 2 electrons is a pair. So I'm sharing a pair here, a pair here, a pair here, and so on. Even more shorthand is like this. CH4 means there's 4 hydrogen atoms, and those are bonded to a carbon atom. Questions on that? We're starting out with the atoms individually. They're not stable because their outer orbital is not full, and then they combine, they share electrons within the outer orbital only to become a molecule. You can see at the bottom what water looks like. Simple water molecule. We have 1 oxygen atom and 2 hydrogen atoms. Hydrogen, 1 proton in the nucleus and 1 electron. They're both unstable. And we have oxygen. Oxygen has 6 electrons, right? If we were to count them up, 1, 2, 3, 4, 5, 6 electrons in its outer orbital. It's not 8, so it's not stable. It's going to take 1 from this hydrogen and 1 from this hydrogen to gain its stability. We'll talk more about water a little bit later. You'll notice these little delta signs. It's the Greek letter delta. Fancy D. It's kind of like a music note. That means partial. And we'll look more at water because it is, we call this the universal solvent. By the way, this was one of the questions that I asked you in the first class when you had to do that quiz. Okay. The universal solvent is water. So there are partial positive charges in water and a partial negative charge. And water, because of that, is polar. It's a good solvent. Substances dissolve quite easily in water. Water dissolves many substances because of its polarity. Partial positive on one end, partial negative charge on the other end. Questions on any of this? Look back because I know I skipped a few, but okay, we've talked about atomic number, we've talked about mass number. You know how to calculate both of them. And the top 2 formulas I wrote already on the board. Actually, I think I wrote the top 3. You need to memorize the top 2 formulas for sure. You memorize the top 2 formulas, you can calculate the last 2. Those are very easy. It's just the rearranging of the formula like I did here, or the logical thinking, however you want to think about it. So you have to know these top 2 formulas. Here are some examples. You can practice with these. Some of that we have already done. Carbon has 6 protons and a mass number of 12. How many neutrons? How'd you get that? So it's just like in math, you have to show your work. I want to make sure you're getting it the right way. Good. So you had to do 12 minus 6, right? Because neutrons does not equal protons. Even though it happens to be the same answer, 6, they don't equal each other. How many electrons? What's the atomic number? 6. Protons, electrons, and atomic number are always the same number. But in this case, neutrons is also the same. Doesn't happen all the time. Hydrogen. You should know this one already. 1 proton, 1 electron, and a mass number of 1. How many neutrons? 0. I didn't even have to tell you all that. I should just be able to say, How many neutrons in hydrogen? And you should know. Just because I've mentioned it at least 5 times already. At least. Okay. 0 neutrons. All right, phosphorus has 16 neutrons and 15 electrons. Getting pretty big. How many protons?
15.
15. Protons equals electrons. What's the mass number? Good. 31. 31. You shouldn't need your calculator. Okay, mass number is just 16 plus 15. Okay. Oxygen, 8 protons. Atomic number of 8, didn't need to tell you that. Mass number of 16. How many, what did I ask for first? Neutrons. 8. How did you get it? Good. 16 minus 8. That's how you got the neutrons. And how many electrons? 8. And like carbon, oxygen is one of those elements of which the protons, the electrons, the atomic number, and the neutrons are all the same number. Doesn't always happen. You will have a few examples like that on your first test, on your first exam. We'll give you just enough information so that you can answer the question. You don't need the periodic table, you should not need your calculator. All right, so we're looking at atoms. Atoms have an equal number of protons and electrons. Positive charges equal the negative charges. An isotope is a different form of an atom. And it's where we are changing the number of neutrons in the nucleus. So it's really not an atom anymore, it's called an isotope. Different form of an atom, where there's a different number of neutrons. If I was to take carbon, which we've already talked about, that has 6 protons and 6 neutrons, and I change the number of neutrons to 7, what's going to happen? If I change the number of neutrons, go ahead. Okay. The mass number is going to change, right? I'm changing the nucleus. I'm changing what's in the nucleus, changing like the weight of the atom, the isotope. So no longer do I have a mass number of 12 like I had before. Now I have a mass number of 13. And we refer to this as carbon 13. Carbon with a mass number of 13. Typically, we will just be dealing with carbon 12. Carbon with a mass number of 12, with the 6 neutrons, 6 protons, 6 electrons, mass number 12. But there are other forms. There's carbon 13, there's also carbon 14. You've probably heard of carbon 14 dating. They find a fossil or find a bone or something, then we could do carbon 14 dating. We could use this isotope to determine how old the substance is. These isotopes that have a different number of neutrons than the original atom will often emit radioactive energy. And if that is the case, we call them radioisotopes. In the term radioisotope, because the number of neutrons is different from what it should be, the atom, the isotope, emits radiation, emits radioactive energy, kind of shoots out sparks. We can use this radioactive energy to our advantage if we were looking at cancer treatment, radiation treatment, radiation therapy deals with using this radioactive energy that these isotopes are spitting out and directing it at your cells that are cancerous. This radioactive energy will kill the cancerous cells. So we can use it to treat a cancerous mass. We can also use it to date, like I said, to see how old something is. We could use it to determine where a particular molecule or atom or hormone is moving or collecting in the body. We can follow its path. We can use it as a tracer. We wanted to know how much iodine is inside of your thyroid, for example, right? We could use that radioactive element, isotope, to trace the iodine, to see how much of it is there. Kind of glows in the dark, so to speak. So we can use these radioisotopes to our advantage. And, you know, for this course, we're really not going to talk more about them other than just this 5 minutes or so. But you should know that they are unstable. The nucleus is unstable because the number of neutrons has changed. The number of protons is the same. The number of electrons has not changed. The atomic number has not changed. But the number of neutrons has changed, and therefore so has the mass number. Yeah.
So in the body, they are basically used to destroy cancerous cells.
You can use them that way, yeah.
But do they do that naturally, or do they need to
Stimulate.
So are all isotopes radioisotopes?
No.
We don't need to know like how
Do not.
you would determine it, right?
Correct. Carbon is just one of the more common. But there are others like iodine, phosphorus, that's isotopes that we only know. Alright, so just kind of switching to look at bonding. We already leaded into this. We already talked a little bit about covalent bonding. With bonding, we're forming a molecule or we're forming a compound. What's the difference between the two? Sometimes they're used interchangeably. A molecule is usually more than one of the same atom bonded together. So if we had 2 nitrogen atoms, that's considered a molecule. Or if we had 2 oxygen atoms bonded together, that's considered a molecule. A compound is when we have 2 different atoms. We have some hydrogen and we have some oxygen. We have some carbon and we have some oxygen, right? We have some carbon, we have some hydrogen, and we have some oxygen. That's a compound. Multiple atoms bonded together, multiple different atoms. But we will often refer to the water molecule as a molecule, even though a molecule should be just the same atom bonded. Does this make sense? Yes? So when we say a molecule of something, we're kind of considering that a unit of something. I will not try to trick you in, using molecule where it should be compound. I'm not going to try to trick you about that. But generally, compounds are different atoms where a molecule is the same. So let's look at ionic bonding. We already saw covalent a little bit, so let's look at ionic. Right? Isotopes were one of those exceptions to the atom rule, right? Where the protons equals the electrons equals the atomic number, and that we could calculate the number of neutrons. Isotopes were kind of a different scenario. Ions are also exception to the rule, different scenario. In an ion, there is a charge. It could be either a positive charge or a negative charge, but there's a charge. The ion is either a cation, cat ions have a positive charge, or it's an anion. Anions have a negative charge. I have a Cl minus and an Na plus. Which of them is the cation? Sodium. Sodium's the cation. Which is the anion? Chlorine. Our anion with our negative charge, our cation with a positive charge. My son wants a cat. He loves cats. I think of that as a positive. Okay, doesn't mean he's going to get one, but cat, positive. That helps you remember it. In an ionic bond, we'll always have an anion coming together with a cation. our pair, our bonded pair, is one's a cation, one's an anion. One's a positive charge, one's a negative charge. So when we put them together, what are we getting? Positive charge and a negative charge. Neutral. Just like we had before with the atom. But this time, in order for them to come together, the positive and the negative charge, we have to change their structure. We're going to change the arrangement of the electrons in the outer electron orbital. We're starting out as an atom, and we're going to an ion. We're going to start out with a sodium atom and a chlorine atom, where we have protons equals electrons, and we're going to change that to make it an ion. We'll have one positive charge and one negative charge. You look first at the sodium atom at the very top. It's in green. How many electrons are in the outer, let's try this again, electron orbital for sodium? One. Anyone disagree? Awesome. Okay, good. One electron in that outer orbital for sodium. Is it stable? No. How many more does it need? It needs 7 more. Chances of that happening? It's probably not going to happen. 7 other hydrogens coming over. No, it's probably really not going to happen. Could be other combinations. So what's going to happen to chlorine? The chlorine atom, which is here in yellow. How many electrons does the chlorine atom have in its outer electron orbital? 7. Oh, 7. All right, so chlorine only needs 1 more then to become stable. Just so happens the sodium atom's right there with its 1 extra one that it has. So they start talking, they strike up a deal. Well, let's see, if you give me your outer electron that you have, then I'm going to have 8 and I'll be stable, and you're going to have 8 and you're going to be stable. They're striking up a deal. So sodium says, all right, I'm going to give you my outer electron. It's just sitting there all by itself. It's lonely anyway, so it doesn't matter. It's just 1. It's like, what, 9 more, 10 more, go. So I'm going to give up that electron. I'm going to donate it. I'm going to kick it out, make it leave. If sodium atom, let's say, gives up 1 of its negatively charged electrons, are the number of protons going to equal the number of electrons? Nope. No, they're not. Because sodium has 11 electrons. Sodium has 11 electrons. That means it must have 11 protons. Still with me? And if it says I'm going to give 1 up, then I'm going to have 10. That means that's not the case. I have now 1 more positively charged proton than I do electrons. So my positives and my negatives aren't neutral anymore. I have a positive charge left over. And that positive charge is right here. That's how you know that you're looking at an ion. If there's a charge written up here, signal that that's an ion. This sodium ion has 1 more positive charge than it does negatively charged electrons. So this one must have been the donator. It donated an electron. Kicked out a negatively charged electron. All right, the chlorine. It had 7 electrons in its outer orbital. Needed 1 more. It had an equal number of protons and electrons, but now it's taken another negatively charged electron. If it's taken another negatively charged electron, now the electrons are going to be higher than the protons. With me? Yes? So the negative charges, the negatively charged electrons, are going to be higher in the chlorine ion because it has accepted the negatively charged electron from sodium. And here's that negative charge. This negative charge says there's now more electrons. There's higher number of electrons here than there was before. This was our acceptor. Accepted that electron. And then we have the two ions. Now they're friends. They like each other. They made a deal. They're partners. But they're not connected. They're close together, but they're not connected. They're not sharing the electrons like we saw before. The electrons are rotating around the carbon and rotating around the hydrogen. That's not happening. We gave one electron up, and the other pair, the other ion accepted that electron. There's no sharing involved in an ionic bond like this. There's an attraction, friendship, I'm going to say it, but no sharing yet.
So the molecule itself isn't an ion. They're two separate ions?
There are two separate ions. The sodium ion and the chloride, it's called, ion, and they're together.
But sodium chloride itself isn't an ion, right?
Sodium chloride is really a compound. Yes, because it's two different atoms, in this case ions, coming together. So, Melissa's right. We are making now sodium chloride, NaCl. The Na is sodium, and because that's an ion, you might also see a positive charge written above that. And the chloride is an ion, so you might see a negative charge written there. Na plus Cl minus.
It's an even charge.
But all together, right? It's an even charge, positive and negative, kind of like an atom, neutralizes itself. And we call this a compound. Remember I said before, if it's N2, it's a molecule, but if it's H2O, it's a compound, because we have two different atoms, two different ions coming together. This is really considered a compound, but we use the term molecule. One molecule of sodium chloride. Yes.
Isn't that covalent bond?
What, this one?
Once you combine the...
So covalent bond is only the sharing of electrons. So only when we're actually sharing, when the electrons rotating around one atom and another one, is it a covalent bond.
You don't have to do it for NaCl.
No, NaCl in itself, sodium chloride, the bond between them is ionic. There's no sharing. It's only a donation and an exception. You could have chlorine covalently bonded to hydrogen, right? Where you'd have a sharing of electrons through both chlorine and hydrogen, and that would be a covalent bond. But chlorine and sodium, the bond between those is ionic. Same thing with sodium. You can have sodium bond to something else covalently, right? You all realize this? That this is just one example with these two ions forming a covalent bond. You could have more substances that could bond to chlorine. It doesn't have to be only sodium. And they could bond with another type of bond. In the case of hydrochloric acid, HCl, hydrochloric acid is a hydrogen atom bonded to a chlorine atom. And that bond is a covalent bond. So instead of the chlorine getting the electron from sodium, it could share the electron with hydrogen. That would be covalent. Questions on the ionic bond? Yeah.
So, like, you have your positive ion,
Mm-hmm.
has to have a corresponding negative.
Yes.
Do they always form?
Ionic bond.
Always.
Mm-hmm.
Okay.
Yep. Anytime you see that plus sign, there's going to be a minus sign there. Many times in the Some textbooks write NaCl, they'll just actually write NaCl like this. You just assume that's an ionic bond. Really, you know, we should be writing it like that. NaCl is the only example I'll give you of an ionic bond. So if you see NaCl, you should know it's an ionic bond. Let's look a little bit more at covalent bonds. I showed you the covalent bond between carbon and hydrogen in methane, which is CH4. And I also showed you the covalent bond within water. We talked a little bit about the partial positive and the partial negative. Covalent bonds involve sharing of electrons. They're sharing pairs of electrons. They can either be single, as is the case that we saw already, single pair of electrons being shared, single line in between the two atoms that are bonded together covalently, or they can be double, means you're sharing two pairs of electrons. We're sharing two pairs of electrons. Now I have two lines connecting the two atoms. That means, how many electrons do I have total being shared? Good, 4. Two pairs of electrons being shared. So 4 electrons total being shared between these two oxygen atoms. We can also have a triple covalent bond. Now I have 3 lines, 3 pairs of electrons. How many electrons? 6. I'm sharing 6 electrons with these 2 nitrogen atoms. Now, for each of the covalent bonds, we can look at what's on either side of the bond, what the atoms are, and what the charges might be, and determine if that bond is a non-polar covalent bond or is a polar covalent bond. It's just like the North Pole and the South Pole are at opposite ends, or you look at the battery. You look at a battery, you see a plus side and a negative side, and if you don't put the battery in right, then the electronic device doesn't work. If we have a positive end and a negative end, then that bond is considered a polar covalent bond. In the case of water, that is the case. You saw before that there was a partial positive side and a partial negative side to water. There were 2 different poles, the plus end and the minus end of the battery. 2 poles, water's polar. The bonds here, these single covalent bonds, are polar single covalent bonds. In the case here with H2, the 2 ends are the same. The electrons being shared here between the 2 hydrogen atoms are being shared equally. So there's really no sides. There's 2 sides, but they're both the same. So that is a non-polar covalent bond. Doesn't have poles. There isn't a plus on one side and a minus on the other side. We're still looking at the sharing of electrons in a polar covalent bond, but the sharing of those electrons, because of the 2 different poles, plus and minus, is not an equal sharing. You're going to share a pair of electrons here. It's going to rotate around oxygen and it's going to rotate around hydrogen, but it's not going to rotate equally. The oxygen, because it's more electronegative, stronger, has a greater pull on the electrons. Think of oxygen like the adult and the hydrogen's like the kids. The adult's going to be in charge. I'm going to get the iPad longer than my son's going to get to use the iPad. But we're sharing it. It's just not an equal sharing. I'm holding on to it longer. So I'm oxygen. The electrons that are negatively charged, I'm holding on to. I'm holding closer to me for a longer period of time. So now because I have these electrons around me longer, closer, I'm more negative. And the hydrogen, my kid, right, it's more positive. He doesn't have the electron that often. So I have 2 poles, 2 ends. Positive and a negative side. I'll show you the picture again. It'll make more sense. So see the way this is drawn here? The electron orbital? It's not a nice circle like it was before. You noticed that? It was a nice orbital, nice and even around the nucleus. And when we shared them in a nonpolar covalent bond, it's nice and even, the distance between the hydrogen nucleus and the orbital, and the distance here. It's nice and even all the way around. But over here, it's elongated. Right? So we're closer to oxygen with those electrons, and we've got to go way out here for that hydrogen. So the hydrogen is by itself longer. And what does hydrogen have in its nucleus? One proton, which has a positive charge. So it's almost as if this hydrogen is just a proton for most of the time. And that's where that positive charge comes from. Same thing happening over here. Oxygen's holding on to these 8 electrons more than the hydrogen atoms are. And I don't know if you can see it or not, but right next to that Greek letter delta is a negative sign. So I have the oxygen over here. I have a partial negative charge on the oxygen. And I'm going to covalently bond it to 2 hydrogens. Each of those hydrogens has a partial positive charge. Does that make sense? So what would happen if I mix water with sodium chloride? If I mix salt and water together, the salt is going to dissolve in the water because water is a good solvent, because water has a negative, partial negative side and a partial positive side. And these 2 charges are going to attract the charges on the ions over here. The sodium ion with the positive charge is going to be attracted to the negative charge up here. The opposites attract, right? That saying, opposites attract. So now I have my sodium ion over here being attracted to this partial negative of oxygen. And what about the chlorine that's negative?
Attracted to the positive.
The chlorine that's negative is going to be attracted to the positively charged hydrogen. And what's water doing now to sodium chloride? It's holding them apart. It's separating the 2. It just broke the ionic bond, essentially. It's separating the sodium ion from the chloride ion. So you don't see the little salt crystals anymore because those ions aren't being, partnered up. They're not next to each other anymore. There's water holding them away. If I have a small amount of water mixed with salt and I let it sit out for the next day, when I come back, at the bottom of my glass, I'm going to see salt crystals again. Why? What happened to the water? What happens to water when you let it sit? It evaporates. It evaporates. The water, maybe from the sun, it's going to heat up, it's going to evaporate, water vapor, it's going away. So the salt now, these ions, can come together again. And you'll see salt at the bottom of the glass. If you've ever had seawater or salt water, you collect seashells, things like that from the beach, you just forget about it, you let it sit, you'll notice there's a whole bunch of salt at the bottom, mixed with the sand and everything else. So water is a good solvent. It can separate substances like this. In other words, it dissolves these substances. If a substance dissolves in water, then that substance is also considered polar. So salt is a polar substance. What's the definition of polar? What does polar mean? Okay, an uneven sharing of electrons. Or what else? Give me another answer. Good. There's a negative side and a positive side. And if we looked at sodium chloride, there is just that, isn't there? There's a positive side and a negative side. So even before you knew about polarity, sodium chloride is a polar molecule. It has charges. It has two different sides to it. And we could test out its polarity by seeing if it dissolves in water. Like dissolves in like. If I mix water and water together, I get water. They dissolve in each other, right? If I mix salt and water together, they dissolve in each other. They're both the same. They're both polar. How about sugar? What if I mix sugar and water together? It dissolves. So is sugar polar or non-polar? It's polar, right? Okay. If I mix oil and water together, oil is non-polar. It doesn't dissolve in water. And so oil would be something like the two hydrogen atoms bonded together. It's the same. It is hydrophobic. Yep, it is a lipid. Lipids are fats. In general, fats are non-polar. Butter or lard or shortening. You think about cooking. Cooking is basically chemistry. Have you ever made salad dressing? You make the good seasoned dressing and you put the seasoning and the vinegar and the water first, and then you shake it up. Why do you think you do that? The vinegar and the water, when you shake it, do you see two layers? Mm-mm. They dissolve in each other. But when you add the oil, then what happens? Then you get two layers because the oil is non-polar and the vinegar and water are polar. And you shake and you shake and you shake and you shake, and it looks like it's coming together, but then you let it sit and eventually it's going to separate out again. You can tell if you look at a solution and a mixture and you see layers that you're mixing non-polar and polar together. From the chemical formula, like this, not really.
Like there'll be if we do, there'll be like some type of like that.
Yeah, I mean, I might show you sodium chloride and ask you if it's polar or non-polar, or sugar, or I don't know, vinegar or oil or butter, something that we mentioned in class. I could ask you, but I wouldn't show you something brand new. I wouldn't show you this, even though this is non-polar. I wouldn't show you a drawing like this and ask you if it's polar or non-polar. But you can think about it as, if it's going to dissolve in water, it's polar. If it's not going to dissolve in water, then it's non-polar. But like dissolves in like. We're always looking for opposite charges, a positive on one side, a negative on the other, then you know it's polar. Unequal sharing of electrons. All right, so we talked about covalent bonds. We talked about ionic bonds. The last type of bond is a hydrogen bond. Hydrogen bonds similar to ionic bonds because there's really no actual link. There's no sharing going on, okay? There's no rotation around here and rotation around here. It's just a weak attraction. I like Christina, so I'm gonna go and hang out with Christina some more. The hydrogen bond is like that. It is a weak attraction. Sometimes it's strong enough for bugs to stand on those bonds, to be supported by those bonds. A bug landing on water, for example, is held on the surface of the water because of the hydrogen bonds between the water molecules. You've all seen that, right? A bug landing on the water. I try to do that and I go straight down to the bottom, right? So the hydrogen bond is not strong enough to support me or any of you, so I don't feel so bad. So the hydrogen bond is shown right here, and often it's shown as a dotted line or a dashed line. That represents a hydrogen bond. So this dashed line or a dotted line, sometimes you'll actually see a little tiny H in the middle here. That's just trying to make it more clear that it's a hydrogen bond. It doesn't mean that there is a hydrogen in the middle of this space. But hydrogen bonds do involve the hydrogen atom. They have to involve the hydrogen atom to be considered hydrogen bonds. It is either hydrogen and nitrogen, like you see here, or it's hydrogen and oxygen. That can be a hydrogen bond. Or hydrogen and fluorine can also be a hydrogen bond. We really won't talk about hydrogen and fluorine though. Not every bond though that involves hydrogen is a hydrogen bond. Okay, we looked at the methane before, the carbon with the 4 hydrogens. Those were not hydrogen bonds, even though they involved the hydrogen atom. They were single covalent bonds. But this one here, this dashed line, that is a hydrogen bond. It's different from this one. The bond here between the hydrogen and the oxygen is a single covalent bond. It's a single polar covalent bond. But in this case, we have this weak attraction between the hydrogen and the nitrogen. The hydrogen is a part of this water molecule, and the nitrogen is a part of this ammonia molecule. And the bond is actually holding these 2 molecules closer together compared to just looking at the hydrogen and the nitrogen and holding those 2 atoms closely together. Do you see what I mean?
Mm-hmm.
It's linking molecules or linking compounds together rather than just atoms. So this hydrogen bond between hydrogen and nitrogen, you might see this in a protein. When we start to look at the second half of this chapter, we talk about the organic compounds. Proteins, one of those organic compounds. Hemoglobin, for example, is a protein, and they're composed of amino acids. Basic structure has this kind of group to it, has this amino group to it. And we can have a relationship between that amino group in a protein, an amino acid, and a water molecule.
So in
So
this
then-
case, sorry, this is the left side is the amino group, the right side is the carboxyl.
Yeah, well, in this particular case, the NH3 is an ammonia molecule. It's just by itself. But you will also see the NH2 or NH group in an amino acid. And in that case, we can form a link between one part of an amino acid, the N group, and the H from another part of an amino acid. And we can link those parts together with a hydrogen bond. It's like taking a big long, balloon and folding it up and twisting it into a horse or shape, right? So rather than it just being flat like this, we can twist it and we can make one end interact with the other end and so on to give it a 3-dimensional shape. That's what happens to your proteins. In order for the protein to function in your body, in order for hemoglobin to bind to oxygen and carry it around the red blood cells, it has to have this particular shape for oxygen to sit kind of right in the middle, like an egg in a basket. And what gives that shape to the protein hemoglobin are these hydrogen bonds that form between the nitrogens on one side and the hydrogens on the other, and so on. Oh, I see a question back.
So I know you said that just because hydrogen is involved doesn't mean that there's a hydrogen bond, but with those 3,
Right.
is there always a hydrogen bond? Like
With
nitrogen and fluorine?
yes,
That's
with those.
always-
What it can be. There can be cases where like oxygen and hydrogen are not gonna hydrogen bond. Instead, they're gonna covalent bond to each other. But the three cases in which you will see a hydrogen bond involve hydrogen, oxygen, hydrogen, fluorine, and hydrogen and nitrogen.
Okay.
It doesn't mean that every bond with those
Has to be.
has to be hydrogen. Yeah. But I will show it to you as either dotted or dashed, so that would be an indicator for you. If it's just a straight line like this one, that's a covalent bond, right? I don't know if red is such a good color, but let me see if blue works. So if I have this protein that's like this, do you all see what I was saying before about the balloon? Right? If I have a protein like this, I can make this protein do something like that because I'll have hydrogen bonds in different areas, linking parts of that protein together. And at these hydrogen bonds, on one side I'll have a hydrogen, and on the other side I might have an oxygen. Or on one side I'll have a hydrogen, on the other side I might have a nitrogen. Does that kind of make sense? You'll see this as we get more into the chapter too. Your DNA is held together through hydrogen bonds. Your DNA, your genetic material in the nucleus of your cells, it's got hydrogen bonds linking it. And mostly the hydrogen bonds you'll see are hydrogen and nitrogen, or hydrogen and oxygen. Those will be the predominant ones that we'll talk about. If we didn't have these hydrogen bonds in this protein, it wouldn't be able to function. There's nowhere for there's nowhere for oxygen to bond to here. But over here, we might be able to stick an oxygen over here or stick some substrate over here.
Then would there be a bond in it, or is it just trapping it?
It's kind of just trapping it. Yeah. If you remember, if you took Bio 105, enzymes speed up reactions. They have a particular shape to them, so that this enzyme will only work with this substance because it can bind to it. It has this little binding site too. It's called the active site. Physically, does it have a covalent bond? No, it doesn't. But it fits within this space. And this space was created because of hydrogen bonds over here. And because of hydrogen bonds over here. Within this whole thing that was a protein. It's like a lock and a key. You have a particular key that fits your car. You have a particular key that fits your, house lock, and so on. The lock, the structure of the lock was made through these weak attractions. You say that they're weak attractions, but they're really, really important. You won't be able to get here if you couldn't get into your car. So dotted line or dashed line is a hydrogen bond. These structures that look like Mickey Mouse, these are water molecules. The red circle is the oxygen atom, and the white circles are the hydrogen atoms. So I have an oxygen and two hydrogen atoms. That's one water, just like I had over here, right? With the negative side and the positive side. This is my negative side. Here's my positive sides. The negative side, notice where the hydrogen bond is going. To this water molecule, which the hydrogen atom is facing, and that hydrogen atom has a partial positive charge. So we have a partial positive charge here, and a partial negative charge over here. Positive and a negative, opposites are attracting, just like we were dissolving the sodium chloride over here. We are linking the two water molecules with the hydrogen bond over here. And we can link one water molecule on this side, one over here, one over here, one over here. One water molecule can link to 4 other water molecules through hydrogen bonds. One water molecule can link to 4 other ones. It's not one carbon atom and 4 other hydrogens. It's one water molecule linking to 4 other molecules. With me? Yeah? Okay. And these are the hydrogen bonds that I was talking about earlier that the bug can land right on top and still stay. Float. Walk on the water. This provides cohesion, strength to the top of the water. Plants use this in order to suck up water from the dirt. The water is moving through the roots of the plant, through the stem, up into the leaves and the flowers. Water moves against gravity to do that, by the way. And the way it stays attracted to each other is through these hydrogen bonds. Questions on that? So we talked about the polarity of water. You can see here the chloride ion being surrounded by all of these water molecules, the positively charged hydrogen pointing towards that negatively charged chloride ion. That was what I was drawing over here. At the very top, that sodium ion up here, it's being surrounded by the water molecules, of which the negatively charged oxygen is facing that positively charged sodium ion. If we look at something and it will dissolve in water, like sodium chloride, it's also polar, then that substance is called a hydrophilic substance. Sodium chloride is hydrophilic because it likes water. In the case of oil, oil does not dissolve in water. It was non-polar. It's called hydrophobic. Phobic. What's a phobia? Right, when you're afraid of something. And so this oil is afraid of water, doesn't like water, doesn't want to mix with water. So we'll have 2 different layers. Questions on the polarity of water?
So when it says can form hydrogen bond, that's because of the positively partial positive charge of that hydrogen.
And the partial negative charge, yeah.
Okay, but that's what's in this combination is what performs.
Because I'm lazy and I don't want to erase, right? So with this water molecule, because I have partial positive over here, I can hydrogen bond this to another water molecule with a partial negative over there. And this same water molecule, because I have a partial negative here, I can hydrogen bond that to some partial positive hydrogen up there. Does that make sense? Same thing over here. I can do that, and I can do another one off this way. Hydrogen bonding, you look at the basic shape of this and multiple water molecules kind of spread out. It almost looks like a lattice, like a snowflake pattern. That snowflake pattern comes from the hydrogen bonds. All right, we'll start with the chemical reactions next time, and we will do pH next time, and then we'll get into the organic molecules, 4 types of organic molecules. Hopefully we'll finish chapter 2 next